Hey class, and welcome back to the end of chapter 6. So I want to just make a short video to kind of expand on and drive home some of the concepts that we discussed in class just today. So anyway, yeah, this is all about airplanes. And so in this part, I want to talk about 6 basic questions. First of all, basically, how do airplanes fly? How can they support themselves? What is with the takeoff process? What is required for liftoff? Something actually particularly unique that's happening during liftoff. What's with the different tilting? If you ever notice, a lot of times airplanes will fly almost looking like they're going straight, but at a slight inclined angle. I wonder why that is. What happens if you go steeper or less steep? What will happen to the airplane? I also want to talk about the wing. If you ever sat near an airplane wing, and if you watch, you can actually see it will change shape at different points in the flight. So I wonder what's the deal with that? Why does the airplane's wing change shape? And then last couple questions are both about what are the mechanisms behind how an airplane controls its flight. How does it turn? How does it propel itself forward through the air? And what parts of the airplane affect that? All right, so now let's try to discuss how an airplane can actually support itself when it's in the air, which this is fascinating to think about, right? An airplane, you, me, everybody in this class, and a bunch of our friends, we could all go pile into a big metal tube, and we could go zooming forward super fast with wings sticking out, and then all of a sudden we can lift off and start to fly. It's incredible, right? We have a bunch of weight, all of us, all of our gear, or luggage and whatnot, the pilot, the airplane itself, all of that has weight. And we can have an upward force being generated somehow by this airplane that's strong enough to overcome, be larger than our weight and make us able to fly. How is that possible? That's what I want to talk about. And as we think about it, ultimately, what's happening with an airplane, again, if we think about how rockets worked, right? They were able to propel themselves forward by pushing off of something. This idea of Newton's third law and or conservation of momentum to describe how things can fly also applies here. In order for an airplane to be moving forward and supporting itself vertically to offset its weight, it needs to be pushing off of something. In this case, it's pushing off of the air. So it pushes air back to propel itself forward, pushes air down to propel itself up. And with those ideas, we can conceptually understand how an airplane is actually able to fly. So it uses this wing shape, as you can see here, a wing at an angle, either a uniform symmetric wing like this, usually for like more fast, smaller planes, or a slightly different shaped wing that we'll investigate later for more commercial airplanes. But regardless of how it is, the airplane is set up in such a way to allow air to be deflected downward, bending air down, pushing upward on the airplane, not dissimilar from how curveballs work, as we talked about, right? If you look at this sort of flow diagram, again, this is an airplane wing, like a cross-sectional cut, just to look at flow around the wing alone and not the rest of the airplane. And so this airplane is moving to the left, and so the air appears to be going over it from left to right. And what we see is underneath the airplane wing, the air is going to hit the bottom of that wing, slowing down, and as the speed goes down, we know pressure goes up, right? Air going over the top has much further to go, so it's going to rush up and over the airplane wing. So on top of this wing here, you're going to have higher speed air and lower pressure as a result, and so you have a pressure difference. There's higher pressure below, lower pressure above, and that generates a net upward force that we call a lift force. So we bend air down, pushing up on the airplane. That's one way to conceptualize it. The second way to think about the same idea is that we're creating higher pressure under the wing, lower pressure above, and that generates a net upward force. Both of those ideas can help us conceptually understand the exact same idea of how an airplane is able to generate lift. So again, we create a pressure difference by deflecting air down, and since air has mass and we give it velocity downward, we must be propelled upward. Really quite fascinating. Now, something interesting about takeoff. If you just have an airplane sitting there, barely moving or moving very slow, you get very symmetric airflow like this, which we kind of talked about with the baseball, right? If you have a slow enough moving ball, you get symmetric airflow and there's no pressure differences. So if you have a slow moving airplane wing, you get symmetric flow and there's no lift being generated. So as you take off, you actually need to do something, or the airplane wing needs to do something to create a different flow, to go from this sort of pattern to the pattern that we were just talking about, where air is actually being deflected down. So here, if we're moving slowly, uniform flow. The airplane needs to do something to actually cause that flow to change, to start deflecting air downward instead of having it kind of fill in behind. And what that is it's what's known as shedding a vortex, which is really just cool. It creates almost like a little whirlpool up at this front point because it's such a tight point, such a small point of contact, builds up high pressure right there that generates this vortex that occurs. And so as the wing starts moving forward, going faster and faster, eventually it's able to create this vortex, which will change the flow. So just to show you what I mean, here's the airplane wing moving forward through the air, okay? If it gets going faster and faster, eventually a little whirlpool, the air trying to rush up over the top, actually tumbles in on itself. It's not able to sustain this type of flow. It tumbles in, creating a vortex. It's like this little whirlpool that you might have seen in a river or something that moves down behind the back of the wing. And that idea, that whirlpool as it goes over, changes the entire flow pattern across the top of the wing and creates a situation where now you have lift. So you go from no lift, you shed a vortex, and then you generate lift afterwards. And that's what's happening as you're accelerating down the runway, enabling you to eventually generate the lift needed for takeoff. Pretty cool. So again, the lift force is usually approximately perpendicular to the direction of the object moving through the air. And so here we see the lift force generated by the airplane wing should be up in order to offset our weight force. So one thing that's interesting to think about, right? If you have an airplane wing flying through the air, cutting through the air, if you wanted to go and take off faster, you think you just tilt that wing up more and more. But what happens is if you tilt the wing too much, you can create a large turbulent wake behind your airplane wing. And what happens if you have turbulence behind the airplane wing? Just like with the baseball, you create a region behind the ball back here that has, or the airplane wing, a region back here that has very turbulent and chaotic flow. So if the air doesn't have time to come up and around the wing and fill in behind, if it doesn't have time to create this type of flow, what you're going to get is a big turbulent wake. And that big turbulent wake results in low pressure behind the wing, high pressure in front of the wing, and now all of a sudden you have this huge pressure drag pushing back against your airplane wing, and that generates a great backwards force, slowing you down, and your airplane drops because your lift is dramatically reduced. And so when you experience turbulence in an airplane, what's happening is you're getting turbulent wake behind your wing, reducing the upward lift, and the airplane drops suddenly, and that's what feels so scary to us. And so when we experience turbulence, it's because a turbulent wake has been generated behind the airplane wing. Pilots will call this stalling because what's happening is the boundary layer, the air flowing over this top, stalls out. It stops moving behind the wing. It stalls right here and tumbles, creating the wake. And so that's why we suddenly drop. But then as soon as you restore the uniform flow, the lift comes back and then you pop back up. And so when this is happening on and off a bunch, you're bouncing around. But the cool thing that helps make it a little less scary is if the pilot is able to adjust the direction of the airplane, then you can always tilt down, decreasing this angle that the wing's at, known as the angle of attack, as shown here. You can always decrease that to return to a nice steady flow. So again, your airplane's going to drop when you feel this turbulence, or what we call turbulence, which is really just a result of the large turbulent wake behind the airplane wing. So the next question was about how does an airplane tilt up to rise and tilt down? Why is it constantly changing the angle that the airplane wing is at? And that's really what we've already talked about. This angle that the wing makes is what we call the angle of attack, and it's constantly changing the angle to change the direction and magnitude of your lift force, because that angle of attack directly affects your lift. So again, if you're going straight into a straight wind, you want to have a certain angle of attack, somewhere around 10 degrees or something, to generate a nice lift to be steady and offsetting your direction of motion. But if you start coming down, offsetting your weight force is what I mean. If you start descending, now all of a sudden the air is coming up from the bottom instead of straight on towards your wing. And so since the direction of the air is changing, the way the lift force is experienced, it also changes. And so your angle of attack, you can be tilted much further down and still have a 10-degree angle of attack as the airplane is descending. Or if the airplane is taking off, you can have, again, a 10-degree angle of attack right here because that's relative to the direction of the wind. And so you can see this is a 10-degree angle of attack, this is a 10-degree angle of attack, and this is a 10-degree angle of attack. All of those are very different positions for the wing, but it really just depends on how the air is flowing around the wing. And so sometimes when we feel turbulence, it's because the direction of air flowing through the atmosphere that we're flying through changes. So the air goes from being horizontal to rising or descending, and all of a sudden that dramatically changes our lift force, and so the pilots have to adjust to that. And if it keeps changing direction a lot, then you're going to keep feeling the different turbulence feelings that you get. So again, we can affect the angle of attack or adjust the angle of attack by just changing the angle of our airplane wing. So one other thing I thought was cool to kind of point out to you all, just like the dimples on a golf ball or the hairs on a tennis ball, airplane wings actually have something known as vortex generators. These little kind of bumps or kind of metal pieces on the airplane wing are there intentionally to create a turbulent boundary layer, to generate intentional small-scale turbulence in order to decrease the likelihood of large-scale turbulence behind the wing. So just like with the golf ball and the tennis ball intentionally creating a turbulent boundary layer to reduce drag, airplanes intentionally create a turbulent boundary layer as well in order to decrease the likelihood of a stall, to decrease the likelihood of an overall turbulent feel and a turbulent wake causing the airplane to drop dramatically. So we, again, create turbulent boundary layers using vortex generators. And here's a picture actually of a car that has the same kind of thing, vortex generators on the back as well. And there's a cool video that I encourage you to go check out if you want to kind of show you somebody doing an experiment with vortex generators. You can actually see the smoother flow created by the turbulent boundary layer. It's really neat. So different airplanes, again, have different style wings. Most commercial airlines have asymmetric airfoils, so ones that are not symmetrical. So as you can see here, the bottom is flat and the top is curved. That's an asymmetric airfoil. This is good for generating very large lifts, okay? And so it's well suited for kind of lower speed and more stable flight like we have in commercial airlines. Symmetric airfoils, on the other hand, like this, those are going to generate smaller lifts but are much more dynamic, able to turn and even do barrel rolls, fly upside down, other things like that more efficiently. And so this is more going to be something that is used in like fighter jets, fighter airplanes, or kind of show planes and things like that. Things that you're not carrying very large loads, you're not carrying lots of people, you're not trying to generate extremely nice, smooth, steady flights, and instead you want to have greater flexibility with your flying. So again, commercial airlines are going to have these asymmetric type foils where you very naturally, even with zero angle of attack, will still generate some lift. And so airplanes can actually change their wing shape. All right, so here's a few different wing shapes that you can see. Again, this is like a cross section, so there's like not a hole in your wing. It's not like falling apart, right? It's attached at different places. But this is just like a cut through in the middle of an airplane wing because there's different pieces of an airplane wing. There's the slat, the vane, the flap, and then the body of the wing. And these pieces are able to kind of move around. They're still attached to each other, but they're able to move, changing the shape, going from this asymmetric airfoil that's flat on the bottom to this almost C-shape style that you have here. So what we have in this situation, we have less curvature. So you're going to generate some lift, but less lift than you would otherwise. But it's good at high speeds because it's going to be very stable, generating a very constant flow and constant amount of lift when at high speed. So that's used when you're up at cruising altitudes. These two, on the other hand, with more curvature, they're going to be able to generate more lift at lower speeds, and so they're good for while you're trying to take off or land, but at higher speeds they become much more vulnerable to turbulence and are not good and not used when flying at really high speeds. So again, picture A is going to be more what you get when you're at cruising altitudes. B or C would be during takeoff or landing. So the next question I had for you all is, how do we actually control the flight of an airplane? And it's ultimately going to come down to using and deflecting air in different directions. All right, so there's various different parts, as you can see in this picture, right? We have this rudder, these elevators, and these ailerons and the propeller. And they're all different parts of how we control an airplane. The ailerons, rudder, and elevators are all used for different aspects of turning, and then the propeller is used to generate our forward motion, as we'll talk about in the next question. But as we think about an airplane, there's really three different aspects of controlling. So there's controlling the tilt of the airplane, all right? And so the ailerons can cause the airplane to tilt left or right. That's these two guys. So you can put one up and one down to tilt. So like if you, let's say like that's the airplane and we wanted to tilt the left side up and the right side down. We would put the right aileron up, deflecting air up, pushing down on the airplane. We'd put the left aileron down, deflecting air down and pushing up, and the airplane would tilt. All right? And so that's what the ailerons are able to do. We use the elevators to control our angle of attack. You can put both of them up, which pushes the back of the airplane down to increase your angle of attack. Or you can put both of them down, deflecting air down, pushing the tail up to decrease your angle of attack. So those are the elevators. And then the rudder can be used to change the direction you're pointing in space. So you can put it off to the left, deflecting air to the left, and pushing the tail of the airplane right, or vice versa. And that's the rudder and how it can be used. All right, so let's think about how each of these can be used in generating the controls for the airplane. For example, which of these do you think is responsible for controlling the overall elevation of the airplane? Well, the elevators, obviously, as the name implies. So again, those are going to be used to change your angle of attack, which allows you to climb or descend, in addition to the engine itself. How fast you're going will also affect your elevation. So both of those together can help control elevation. And which do you think are more responsible for your direction and how you turn? Well, I'm guessing you could guess by now that those are mostly going to be about the ailerons that tilt you left or right, because if you tilt, then your lift is off at an angle and you're able to turn, or you can change how you're pointing with the rudder to also control your direction in space. And so you can turn and or change your direction you're pointing in space. And so this is a little clip that NASA has put together that I found that I thought kind of drives this idea home just a little bit. So I just wanted to show this to you really briefly here. So there's the ailerons. You can see how they cause the plane to adjust its tilt, which you can use for turning. Usually one goes up and the other down, so that you get forces on both wings to help change that angle. There's the elevators going, pushing the angle of attack up or down, depending. Those two usually will work together in the same direction. And then you also have the rudder here, which it didn't show, but the rudder would again be changing where you're pointing in space as well in the other direction. And so the last question we had, just to kind of wrap up, to try to keep our video to about 20 minutes or less here, is how does the propeller itself actually propel your object forward? And it's really cool. With a propeller plane, basically, as you can kind of see in this picture here, is it basically just has these big spinning airplane wings. Those wings, again, have the same shape, that asymmetrical airfoil shape, and as they're spinning and cutting through the air, they're deflecting air backwards, pushing the airplane forward. So again, the propellers are just like spinning wings, pushing air back and causing yourself to move forward. So overall, that propeller is pushing the air back. It's doing work, burning fuel. If we think about conservation of energy, it's burning fuel using that chemical potential energy to spin your propeller, and as it spins the propeller, it's pushing on the air, adding kinetic energy to the air backwards, which then propels and pushes your airplane in the forward direction. So you're pumping air back and it pushes you forward. Turbojets are slightly different, the big things that you'll see on the wings of most commercial airplanes, but it's the same basic idea. They're using chemical potential energy, burning fuel, to take air in the front and accelerate it and shoot it out the back. It just uses different mechanisms rather than a spinning blade. It has more complex mechanisms that are going on to capture the air, compress it, add thermal energy as it burns, and shoots it out the back. But it's still the same basic idea. So anyway, that wraps up kind of the introduction to how flight goes, and that actually wraps up chapter 6. So soon we'll be moving on to chapter 7, which is all about thermodynamics. Get excited.